Now we are diving on hands-on with Python. Open VS Code. Download CSV from the given link in description below. Save it in a folder. Navigate to the folder in which you saved the CSV file and open VS Code in that folder. Now click on New File icon in VS Code and open New File model.ipynb. Step 1. Install libraries. Let's begin by installing the necessary libraries. These libraries will help us with data manipulation, building the machine learning model, and creating visualizations. First, we need to install Pandas to manage and manipulate the data. To install it, open your command prompt or terminal and type pip install pandas. This will install the Pandas library on your system. Once Pandas is installed, we also need scikit-learn for machine learning algorithms and matplotlib and seaborn to create beautiful plots for visualizing our data. To install scikit-learn, type pip install scikit-learn in the terminal. Next, let's install matplotlib for visualizations. You can do this by typing pip install matplotlib. Lastly, to improve the appearance of our plots, we need seaborn. To install it, type pip install seaborn. Step 2. Load and clean the data. Now that we have all the libraries installed, it's time to load our dataset and clean it up. We will load the dataset into a Pandas data frame and remove any rows with faulty or missing data. To begin, let's import Pandas and load the dataset. You will write import pandas as pd, and then use pd.read_csv, heart_disease_data.csv, to load your dataset into a data frame. Make sure to replace heart_disease_data.csv with the correct file path of your dataset. Next, we need to remove any rows with faulty data. Some values in our dataset are incorrect, so we filter those out. For example, if the CA column has a value of 4, we remove that row, as it's not valid. To do this, you'll write df is equal to df CA is equal to 4. Similarly, if the tile column has a value of 0, we remove that row too. You can filter it with df is equal to df Kyle is equal to 0. Lastly, if any columns have missing values, we need to handle them. To fill in missing values, we will use the median value for each column. To do this, you'll use df.fillNA, df.median, in place is equal to true. This ensures that our dataset has no missing values and is ready for analysis. Step 3. Exploratory Data Analysis, EDA. Now that our data is clean, let's explore it visually. This step will help us understand the distribution of features and their relationships with heart disease. We'll create several plots to analyze the data. First, we need to import matplotlib.py plot and seaborn for plotting. You will type import matplotlib.py plot as plt and import seaborn as SNS. Next, let's set up the style for our plots. To give them a clean and professional look, we will use sns.set, style is equal to white grid. Let's now plot the distribution of 3 key features, age, cholesterol, and maximum heart rate. We'll display each feature in a separate subplot. For this, we'll use plt.subplots 1, 3, fixays is equal to 18, 5, to create 3 subplots side by side and set the size of the figure. To plot the first feature, age, we will use sns.histplot, df, edge, kd is equal to true, ax is equal to axis a 0, color is equal to sky blue. This will create a histogram of the age column with a kernel density estimate, KDE, to show the distribution. We then set the title of this plot with axis a 0, set_title, age distribution, . Next, we'll do the same for cholesterol. We will use sns.histplot, df, chol, kd is equal to true, ax is equal to axis 1, color is equal to green, to plot the distribution of cholesterol. Similarly, we set the title for this plot with axis 1, set_title, cholesterol distribution, . Finally, we'll plot the maximum heart rate distribution using sns.histplot, df, collage, kd is equal to true, ax is equal to axis 2, color is equal to orange. Again, we set the title for this plot using axis 2 dot set underscore title, max heart rate distribution dot. Once the plots are set, we use plt dot tight underscore layout to ensure they don't overlap and plt dot show to display the plots. Step 4. Correlation heat map. Now, let's take a closer look at the relationships between the features. A correlation heat map will help us understand which features are most strongly related to each other. To create a correlation matrix, we can simply type correlation underscore matrix is equal to df.core. This calculates the correlation coefficient between each pair of features in the dataset. Next, let's create the heat map. To do this, write plt.figure, figsize is equal to 12, 8, to set the size of the heat map. Then use sns.heatmap, correlation underscore matrix, nnet is equal to true, fmt is equal to .2f, kmap is equal to coolvorm, linewidth is equal to 0.5 to generate the heat map with correlation values displayed in each cell, rounded to 2 decimal places. We also choose the color palette coolvorm for the heat map. Finally, use plt.show to display the heat map and visualize the relationships. Step 5. Preprocessing the data. Before we start building the model, we need to preprocess the data. This includes encoding any categorical variables and splitting the data into features and the target variable. Let's start by encoding categorical variables like sex, CP, chest pain type, and time, thalassemia. To do this, we will use label encoder from scikit-learn. First, we need to import it with from sklearn.p our eprocessing import label encoder. Next, we initialize the encoder with label underscore encoder is equal to label encoder. Then, we use label underscore encoder dot fit underscore transform to encode the columns. For example, to encode sex, you will write df sex is equal to label underscore encoder dot fit underscore transform df sex. Similarly, encode CP, restec, exeng, slope, and tile columns. Step 6. Split the data into training and testing sets. Now, it's time to split our data into training and testing sets. The training set will be used to train the model, while the testing set will evaluate its performance. This ensures that our model can generalize well to new data. To do this, we use train underscore test underscore split from scikit-learn. First, import it with from sklearn.modal underscore selection import train underscore test underscore split. Next, we separate the features x from the target variable y. For the features, we drop the target column with x is equal to df.drop, columns is equal to target, and for the target variable, we select just the target column with y is equal to df target dot. Finally, we split the data into training and testing sets using x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split, x, y, test underscore size is equal to 0.2, random underscore state is equal to 42. Here, we use 80% of the data for training and 20% for testing, and we set the random underscore state for reproducibility. Sure. Here's the continuation of the narration for testing the model. Step 7. Build and train the model. Now that our data is preprocessed, it's time to build and train our machine learning model. We'll use a classification algorithm to predict heart disease. And in this case, we'll go with the popular logistic regression model. To begin, we need to import the logistic regression class from scikit-learn. Write from sklearn.li near underscore model import logistic regression to import the model. Now, we can initialize the logistic regression model by typing model is equal to logistic regression. This creates an instance of the model, ready to be trained. Next, we train the model using the training data, x underscore train and y underscore train. You can do this with model.fit, x underscore train, y underscore train. This will fit the model to the training data, allowing it to learn the patterns and relationships in the data. Step 8. Test the model. Once the model is trained, we need to evaluate its performance using the testing data. This will help us understand how well the model generalizes to unseen data. To test the model, we will make predictions using the predict method. For this, write y_predict is equal to model.predict x_test. This will generate predictions on the testing set, which we can then compare to the actual values. Now, let's evaluate the model's performance. We will use accuracy, precision, recall, and F1 score as the metrics. First, we need to import the required functions. To do this, write from sklern.metrics import accuracy_score, precision_score, recall_score, F1_score. Let's calculate the accuracy of the model with accuracy is equal to accuracy_score, y_test, y_pred. Accuracy tells us the proportion of correct predictions out of all the predictions made. To calculate precision, which measures how many of the predicted positive cases are actually positive, type precision is equal to precision_score, y_test, y_pred. To calculate recall, which measures how many of the actual positive cases were correctly predicted, type recall is equal to recall_score, y_test, y_pred. Finally, let's calculate the F1 score, which is the harmonic mean of precision and recall, giving us a balanced measure of performance. To do this, write F1 is equal to F1_score, y_test, y_pred. Once we have all the metrics, we can print them to evaluate how well the model performed. You can print the results using print, accuracy, print, precision, print, recall, and print, F1 score, F1. Step 9. Confusion matrix. Let's also take a look at the confusion matrix to understand the types of errors the model is making. A confusion matrix shows how many true positives, true negatives, false positives, and false negatives were predicted by the model. To generate the confusion matrix, we need to import it. Type from sklern.metrics import confusion_matrix. Then, we can generate the confusion matrix by typing cm is equal to confusion_matrix, y_test, y_pred. To visualize the confusion matrix, we can use Seaborn's heatmap function. Type sns.heatmap, cm, nnet is equal to true, fmt is equal to d, cmap is equal to blues, xticlables is equal to no disease, eticlables is equal to no disease. This will display the confusion matrix with appropriate labels and colors. Finally, use plt.show to display the heat map. Step 10. Final thoughts. Now that we've built and tested our model, you should have a good understanding of the key steps involved in a machine learning project: data loading, cleaning, exploratory data analysis, model building, training, and evaluation. Remember, in real-world projects, you likely need to try out different models, tune hyperparameters, and perform more advanced techniques to improve your results. But this is a great starting point. As you continue practicing and working with different datasets, your skills in machine learning will grow, and you'll be able to handle more complex problems with ease. Thanks for following along. Be sure to experiment with different datasets, models, and evaluation techniques to improve your skills and understanding of data science.